Hi, everyone. Thank you for your time and hope all of you are safe and happy and not bored like me. My name is Behnam. I've been doing video since 2010 in various different companies that you've probably never heard of. And currently, I am the video R&D lead engineer at The Evolution. And The Evolution is basically the leading B2B provider of live casino systems since 2006. We have offices and studios in 20 different countries. We are having and operating more than 800 tables, and each of those tables are basically a mini studio with live streams 24/7. And we are having operations globally 24/7, obviously. I'm part of the video team at The Evolution. Our video team and me, we are based in Riga, Latvia. This is a team of 32 people, including management, QAs, and engineers. We are tasked with delivering the live video worldwide with the glass-to-glass latency of 1.5 to 3 seconds. We are mainly delivering the video over the WebSocket to the Android and the desktops and HLS to the iPhones. And we are doing it through our in-house developed platform. And we are owning all the aspects of the video streaming, including the capture, encode, distribution, and playback. And our main job is basically to fulfill the requirements of our games, including the adaptive quality, bandwidth restrictions, latency requirements, and some other extra stuff as well. So what does a typical and regular game scenario works? In this case, for example, in a regular roulette, we are making sure that we are adhering to that standard latency of 1.5 to 3 seconds. We are offering the adaptive quality, seamless switching in case of HLS, of course, and on our WebSocket delivery as well. And in a regular, for example, roulette, users may join at any time to the game, but they cannot actually start playing it and they have to wait for the rounds. And that means that as soon as the ball drops, a round is finishes, and then users can basically play. A regular game like that looks like this. We are having a single encoder, which is ffmpeg-based. We are generating multiple renditions using the RTMP, pushing it to the cloud, and then over there to the devices and users. Uh, Obviously, there are so many bits and pieces in between, but that's the general gist of it. But sometimes, with the help of our game designers, we are facing with new challenges, and we have to face them, and we have to fulfill whatever that's needed. And in this case, it's the new game that's called Instant Roulette. Well, we've been working on this game since 2019, and it became live last year in 2020. And the aim of this game was to remove the waiting time between the game rounds. It consists of 12 roulette wheels. Each wheel has its own dedicated video and audio, basically a camera above each wheel with own microphone. And there's one camera that provides the global view of all the wheels. Users start playing at their own pace, at their own time, and whenever they push the button, literally, then the video should switch seamlessly to the wheel closest to the drop ball. And that means switching the whole video stream. And different users at any time, because they may press that button at different times, they may switch to the different stream. And as part of the requirements, wheels should be and could be added or removed on the fly. These are mechanical devices, they need regular maintenance, and for the sake of just one wheel, we cannot stop the whole game. So that's part of the requirement. We should be able to add the video streams on the fly during the production. So what it looks like, it's like this. There are multiple independent encoder instances that they could be either on a single machine or multiple machines. You can imagine 13 instances, each one of them like 4 or 5 qualities. It should be a huge machine that can support that. So inevitably, they will be residing on the different encoder machines. And different users may see different streams based on the timing of their gameplay. So this is how the studio looks like. There are 12 wheels, each of them has a number, and there's a camera. Obviously, in this photo, you cannot see them. They are out of the frame. But each camera has partial view of the neighboring wheels, basically. So we needed to have sync for so many obvious reasons. First of all, is that the sync is needed because we need that each and every one of those instances represent the same moment in time. That is absolute requirement for the integrity of the game. I mean, users, when they're switching to a specific wheel, they will see partially other wheels as well. And in the global view, they can see everything. So if there's jump around or freezes or anything in between, then that may hurt the trust of our users. Also, there is a music and each and every one of those streams. This is the same music everywhere, obviously, but if these videos are not synced together, then there will be jump in the music that the users are going to hear. That's obviously a very bad thing. And also on the serving side of the things, our media packager basically uses the timestamps to determine when to switch to different quality and different, in this case, different video feed from different wheel. And also media player needs aligned keyframes for seamless switching. Again, if you think about it, switching between the different streams and different quality, it's exactly the same thing on the player side, at least. And for the single encoder streams, like it's streams coming from a single wheel, the timestamps are already aligned. And that's because they are all using the same input and they are using the same buffer. So it's obvious that they should be aligned. It is natural. And the keyframes are also aligned, as it is very necessary for the adaptive quality. But what about the separate encoders? Because usually the different encoders on different machines, there's no guarantee that they are going to start at the same time altogether. And also, as part of the requirement, we should be able to add and remove and start and stop encoders in between the production when it is live. So how did we do the sync? Well, we started by using the wall clock as a reference. That means that there's no master stream, and all of the other streams have to sync with that. Rather, there's a wall clock that is used as a reference. And for that, we are using an NTP server. All of the encoder machines are synced with that same NTP server. And we set a specific date and time as origin. For example, every Friday at noon. And we calculate simply the time passed from that origin time, Friday noon, and by subtracting the origin from the current time, and in milliseconds. You might ask why we don't use the NTP time, basically. That's because in milliseconds it will be a huge number, and we needed a small one to be able to embed it in our as PTS, basically. And we use that difference as timestamps. So it looks something like this. The timestamps are the difference between now and Friday noon, and basically all of the frames now should have the exact same time, right? Regardless of the time that they are joining. And this is how it looks after that. The quality of this video is not good because it's being captured by a mobile phone camera by the QAs during the development and testing in 2019. And you can see when the stream is switched, there's a freeze there. I'm replaying that. You see that the wheel is spinning and there's a freeze. That zoom is just a JavaScript thing. It's not a part of the video. It's on the player side. And let me play it one more time. And you see the freeze is happening. And you might already guess what is the problem is there. That is because the timestamps are indeed in sync, but the encoders are not starting it exactly at the same moment. Therefore, the keyframes are not in sync. Therefore, there is video freeze when switching to another stream which doesn't have an aligned keyframe at the exact time in the moment. HLS will also suffer. Basically, every adaptive streaming, every other protocol will suffer in that case because we cannot switch to anything other than keyframe. That these are basic facts, basically. So the fix was basically to get these keyframes in sync. And it is really hard to guarantee the exact timing. Also, when a single wheel is out of order and we want to restart it, it doesn't make sense to stop all the other 12 streams just to stop and start another one. So what we've done was that basically we calculate proper timings that it is proper for the encoder to start based on the gap sizes. In this case, we are showcasing a 1 second gap size. And when we are starting the encoder, we are simply dropping input frames until the next keyframe time intervals. And we are doing that through LibAV device and through the capture card interface, which is black magic, basically. And how does it look like after that fix? It looks like this. This is the real video captured like a few days ago. And you see that the switching is happening pretty seamlessly. And if you look closely in global view, one of the wheels is already out of order, the wheel number 5. It's been down for maintenance. That was quite by coincidence, actually. You see that the switching is happening pretty neatly. And that's a good thing, definitely. So what about the drift? I mean, if you're doing a stream for a few hours, that might not be a big issue. But when you're doing it for 24/7, then drifts are inevitable. They are going to happen. So how did we compensate for that? Pretty simply, actually. We have the start time of the encoder. We know the number of frames that's being encoded since, and we know the duration of each frame. So we can calculate the proper timestamps. That means that the start time plus number of frames multiplied by frame duration. And we have that proper timestamp, basically starting time at any moment. And we're very regularly checking that and rechecking that. And if the time is drifted forward, basically, we are dropping frames, or if it is behind, we are simply duplicating to compensate for that. And if you're doing it, and we are doing it pretty regularly, then there won't be much of artifacts like jumping or freezing due to dropped frame or duplicated frames, because the changes is as small as few frames, 2-3 frames, and it will fix that. And one thing that I did not put in the slide is that there might be other use cases for this same thing, like creating redundancy for critical streams that you might need for maybe more than one. If one goes down, we can switch to other ones seamlessly. But since that was not, and that is not our use case in this case, so I didn't put it in the slide. So thank you for your time.